Introduction to Programming. Frame 1. Since man's earliest days, we've had a communications problem. Sometimes the results of early man's inability to communicate were disastrous, especially for man. But no matter how complex early man's language problems were, they seem minor compared to the barrier we encounter trying to communicate with our computer. Our language consists of words such as add and store. Although these simple words are easily understood by other English-speaking people, they mean nothing to the computer. You see, the computer, since it's a machine, only understands machine language. To illustrate the difference between man's language and machine language, let's examine a simple program. On the left, we see a program that adds A and B, and then stores the sum. At the right, we see what the same program looks like in machine language. Imagine trying to decipher many pages of machine language. Frame 6. Nevertheless, when computers were in their infancy, this is exactly the way we communicated. Machine language programs were entered with binary switches. This was a very cumbersome process. Programming errors were the rule rather than the exception. The introduction of the keyboard simplified data entry. Now machine instructions could be expressed as hexadecimal or octal numbers. As shown at the top, the hexadecimal number is entered via the keyboard. The keyboard converts the hexadecimal number into binary numbers or bit patterns that the computer understands. As shown at the bottom, a similar process is used for octal numbers. With this method, less key closures are required, and the program can be entered faster than with binary switches. Although the keyboard is a big step forward, it still has its drawbacks. Since the keyboard only inputs hexadecimal numbers, we must convert each operation and number into hexadecimal. This requires the use of a special chart called the opcode table. Take, for example, the add operation. The opcode table shows that the code for the add instruction is 8B. Therefore, each instruction or operation must be converted into hexadecimal, as must all data. To compound the problem, one opcode table may contain more than 100 different opcodes. By now, you probably see the problem. To write a program for keyboard entry, you must first write the program in terms you understand. Then you must look up the appropriate opcodes in the table and rewrite the program in hexadecimal. A step up from machine language is assembly language. Assembly language has two distinct advantages over machine language. First, each instruction is represented by a mnemonic. The chart at the left shows a couple of mnemonics we might find in an instruction set. Notice the mnemonic for the load accumulator instruction. It's LDA. Also check the mnemonics for the add, subtract, store accumulator, and halt instructions. Each mnemonic can easily be identified with the associated instruction, and after you use them a few times, you'll find them easy to remember. On the right, we see the assembly language program for the simple addition of two numbers. Once we understand the mnemonics, the program is easily understood. Another big advantage of assembly language is that we can use symbolic addresses. Notice the use of terms such as VAR1 and VAR2 that represent the two variable numbers we want to add. There's no need for the programmer to assign specific memory addresses for each variable. The computer does it for us. Frame 11. Of course, the mnemonics and symbolic addresses used in assembly language are alphanumeric, meaning they are made up of a combination of letters of the alphabet and numbers. These alphanumeric characters cannot be entered with the octal or hexadecimal keyboard. Instead, they must be entered with a typewriter terminal. Two popular alphanumeric input-output devices are the teletypewriter, shown on the left, and the video terminal, shown on the right. With the teletypewriter, the keyboard is used to enter data. Computer output is typed on paper, producing what is commonly referred to as hard copy. Thus, the teletypewriter produces a permanent record. The video terminal looks like a television with a keyboard attached. Data is entered with the keyboard and is displayed on the television screen. Naturally, the teletypewriter and video terminal are more expensive than the simple octal or hexadecimal keyboards. Nevertheless, these expensive input-output devices are necessary if we're to enjoy the advantages of assembly language. Now remember, the computer only understands machine language, a series of ones and zeros. Therefore, once you've written the original program, called the source program, it must be translated into machine language. The computer can make this conversion if we supply it with a translation program. It's done like this. The source program on the left is compared with the translation program in the center. The translation program is known as the assembler. Notice that the assembler contains the mnemonics and the corresponding binary numbers for each mnemonic. When a mnemonic is loaded, the computer searches until it identifies that mnemonic. It then selects the corresponding binary numbers. The final result is shown on the right, a compilation of the source program written in machine language known as the object program. The mechanics of the assembly process are shown here. First, the assembler is loaded into the computer and stored in memory. Next, the source program, written in assembly language, is loaded and likewise stored in memory. Now the computer runs, translating the source program into machine language, producing the object program. Notice that this process does not execute the program, but merely changes it into machine language. The big drawback to assembly language is that it is machine dependent. You see, the mnemonics for one computer seldom match those of another. Therefore, a program assembled on computer A probably won't work on computer B. Frame 16. Now we're really in the big leagues as far as computer languages are concerned. This high-level language is known as compiler language. Compiler language is machine independent, meaning a program written in compiler language can run on virtually any computer. All that's required is a program called a compiler. Also note the compiler statement shown at the left. It's written in terms we use every day, so it's easily understood. Here we see three types of compiler languages: Fortran, COBOL, and BASIC. Fortran is a contraction of the words formula translation. Likewise, COBOL is an acronym for the Common Business-Oriented Language. BASIC is an acronym for Beginner's Algebraic Symbol Interpreter Compiler. Or you may hear BASIC referred to as an acronym for Beginner's All-Purpose Symbolic Instruction Code. Let's look at each of these in more detail. Fortran is designed with a mathematician in mind. It accepts algebraic type equations that can range from simple to complex. Here we see a few of the mathematical symbols that are used with Fortran. The operation associated with each symbol is shown in the center, and an example is shown on the right. The Fortran symbols for add, subtract, and divide are symbols we use every day. The symbol for the multiply operation is the asterisk. Notice the symbol for exponentiation. It's two asterisks. The example at the right shows how this expression would be written to square the variable x. As shown, SQRT represents the square root operation. At the bottom we see a typical Fortran statement. Here we see examples of symbols used in BASIC. BASIC is very popular with small computer users. Notice the similarity between these BASIC symbols and those used in Fortran. The only differences are the exponentiation symbol, represented by the arrow, and the square root symbol, SQR. At the bottom, we see a statement written in BASIC. Frame 21. COBOL is a compiler language for business applications, where large amounts of data are to be handled. For example, COBOL might be used to generate paychecks for a large company. On the left, we see a few sample operations used in a COBOL program. At the right are sample COBOL statements. The statements use everyday language and are easily understood by non-technical people. Here we compare sample statements written in all three compiler languages. At the top we see Fortran, BASIC, and COBOL statements. All produce the same result. At the bottom are simple programs in each language that will compute the area of a circle with a radius of 2. But we're still saddled with the problem that the computer only understands machine language. Therefore, our source program must be compiled in machine language. The compiler process is similar to the assembly process. At the left is the source program, in this case written in BASIC. In the center is the translation program, naturally called a compiler. The compiler converts source program instructions into machine language. Notice that unlike the assembler, the compiler can translate one instruction, such as let R equal 2, into many machine language instructions. The final result of translation is the object program on the right. Here's the mechanics of compiler language. First, as shown at the top, the source and compiler programs are loaded in the computer. The program is compiled, and the output is the object program. But notice that we still have not executed our program. To do this, we must perform the sequence shown at the bottom. The object program and any data required are loaded into the computer. The program runs, and finally we receive the results of our programming effort. This system is excellent for large computers, where computer time is expensive. However, the compiler does not allow direct interaction between the operator and the computer. Fortunately, there is a language that permits direct interaction with the computer. It's called interpretive language. Interpretive language is very popular with computer hobbyists who want immediate problem solution. Frame 26. With interpretive language, the source program can be loaded directly into the computer, and the computer produces immediate results. In interpretive programming, the input is usually the typewriter keyboard. Output is via video display, as shown on the left, or printed hard copy from the teletypewriter. The advantages of interpretive programming are shown on the right. They are direct access to the computer, immediate problem solution. Programs can be constructed, tested, and debugged statement by statement. You can compose either partial or complete programs, and probably most importantly, communication with the computer is in source language. Notice that BASIC can also be an interpretive, or as previously discussed, a compiler language. Now let's review what you've learned about computer languages. Make sure that you have paper and pencil handy. When you've answered all the questions, check your answers against those listed in frame 29. If you answer a question incorrectly, go back and review that section of the tape. When you're satisfied that you know all the material, turn on your recorder and continue the program. Okay, at the tone, turn your recorder off and begin the review test. Welcome back. Frame 30. One important point that should be firmly entrenched in your mind is, if we're going to use the computer, we must write programs. This is called programming. Essentially, 5 steps are followed when developing a program. First, we must define the problem. Second, we must flowchart or map the solution. Now we can write the program using the flowchart as a guide. Next, we debug the program trying to remove any errors. Finally, we run the program and obtain the results. To develop the skills required of a programmer, we must put the computer into proper perspective. First, the computer knows nothing, yet it has the capabilities to do many things. We might compare the computer to an infant child. Until it's told exactly what to do, the computer can't even add the numbers 3 and 5. We have to teach the computer how to add, and the instructor is our computer program. The way we teach or program the computer to add is similar to the teaching method we use with our children. As shown on the left, we begin by teaching number recognition. Once the numbers are identified, we move on to the process of addition at the right. Here the child is taught the proper sequence of addition and the resulting sum. Let's briefly examine the process we use to add two numbers. Of course, most of these steps are done subconsciously. We begin by writing down the first number, in this case a 3. Next we write down the second number, a 5. Now we place the plus sign at the left of the second number, and then we draw a line below the numbers. The fifth step is the process of addition, and we recall that the sum of 3 and 5 is 8. Then we write down the sum. Our computer adds numbers using a similar procedure. First, the computer reads in the numbers. The numbers are added, resulting in the sum. Finally, the computer prints the sum. Note the distinct procedure. Nothing is left to doubt. As a programmer, you must tell the computer step by step what you want it to do. If we chart each step the computer takes in our simple addition problem, it looks like this. Each block represents one computer operation. The arrows between blocks represent the flow of computer operations. Therefore, the entire sequence is known as a flowchart. Hence, the flowchart represents the computer procedure. Frame 36. Before we get more involved in the process of flowcharting, let's nail down some important concepts concerning computer programming. First and foremost, the computer does not solve problems. The computer programmer does. Once a programmer solves a problem, it can be turned over to a computer for rapid processing of large amounts of data, and this is the real advantage of a computer. Second, the programmer usually draws a flowchart that shows the step-by-step procedure the computer will follow. The process is called programming. The final result is a program. A flowchart is similar to a blueprint. No self-respecting carpenter would attempt to build a house without a complete set of blueprints. Such a venture would probably result in the house shown on the left. Given a well-designed blueprint, so nothing is left to doubt, the finished product will be the house on the right. Notice that the blueprint is drawn using standard symbols for doors, windows, and so forth. Therefore, the blueprint can be read by any carpenter. The flowchart is like a blueprint. If drawn correctly, the program produces the desired result. Agreed, there are times when the flowchart isn't necessary, especially if the program is simple. But if you undertake a complex problem, the flowchart is a must. Like the blueprint, a flowchart is drawn using standard symbols. Here we see 5 symbols used in flowcharts. Although there are many other flowchart symbols, these 5 are the most common. Let's look at each of these in more detail. All flowcharts have a beginning and most flowcharts have an ending. These are the terminal points, and they are represented by the terminal symbol shown on the left. At the right, we see 2 examples of terminal symbol use, a start and a stop. The operations box shown at the left is probably the most frequently used flowchart symbol. It represents a logical process, such as loading or moving data, algebraic processes like addition or multiplication. It can also be employed for such statements as print or set. Another key point to remember: if you have a process that is not specified by one of the other symbols, use the operation box. The diamond-shaped decision box is really the heart of the flowchart. It allows a logical choice between two conditions and therefore controls the direction of flow. If a condition is satisfied, the yes route is taken. If the condition is not satisfied, the no route is selected. Typical examples for the use of a decision box are shown on the right. Notice that the yes route can either be from the side or from the bottom. Flow lines tie the flowchart symbols together. As the name implies, they represent the flow of the procedure. Normally, flow is from top to bottom, or from left to right, but no firm convention is applied. They can just as well point in the opposite direction. The connector's function is implied by its name. It connects one part of the flowchart to another. Two typical uses of the connector are shown on the right. The first use occurs when our flowchart spills over onto another page. A connector is inserted and labeled, in this case 1A. We continue our flowchart on page 2 with a connector again labeled 1A. Another example is shown by connector 2A at the bottom of page 2. Suppose we want the flowchart to repeat. We simply place a connector at the end of the flowchart. This connector branches back to the beginning of the program on page 1. Frame 44. Usually, sophisticated flowcharts use shorthand mathematical symbols to represent decision-making processes. Here are 5 commonly used symbols. An example of their use and a description is at the right. The equal sign is self-explanatory. The second symbol represents greater than. In the example shown, the expression states that A is greater than B. Symbol number 3 means less than. Therefore, the example states A is less than B. The fourth symbol is a combination of the greater than and equal symbols. An example would be stated as A is greater than or equal to B. Symbol number 5 combines the less than and equal symbols, producing an expression that says A is less than or equal to B. Decision-making symbols are usually found in decision boxes. Let's look at a few examples. The example on the left asks the question, is A greater than 14? A yes answer indicates that A is greater than 14, while the no routine will be taken if A is either 14 or under. Moving to the right, the decision box asks, is A less than 10? The yes route indicates that A is 9 or under. Likewise, a no means A is either 10 or higher. The example on the right says, is A greater than or equal to 100? Naturally, a yes is indicated if A is 100 or higher. On the other hand, if the answer is no, A is less than 100. Now that you recognize flowchart symbols, let's try a couple of flowcharting problems. The first problem is shown on the left. We need to write a flowchart that will allow the computer to add 3 numbers identified as A, B, and C, producing the sum S. Then we want the computer to print the sum. The mathematical expression for this problem is shown at the bottom. The simple flowchart on the right solves this problem. Our flowchart begins with the start terminal symbol. Next, we find an operation box that tells the computer to read A, B, and C. This process loads the numbers into the computer. Then the computer is told to add A, B, and C, giving S. This process does a couple of things. First, it adds the 3 numbers. Second, and just as important, it identifies S as the sum of A, B, and C. Now we tell the computer to print S. Finally, the computer is told to stop. Let's move on to a somewhat more complex problem, that of traffic control. On the left, we see a drawing of a typical traffic intersection. Main Street is busy, while Side Street handles a moderate amount of traffic. A traffic study shows that if traffic on Main Street is allowed to move for 2 minutes, while the traffic on Side Street is allowed 1 minute of flow, the intersection controls traffic very efficiently. Now we've arbitrarily assigned light A for control of Main Street and light B for control of Side Street. Before we jump immediately into the flowchart, let's examine what each light must do. Light A, shown at the top right-hand side, must be green for 2 minutes. Naturally, we want a caution light between red and green, so we've selected a yellow duration of 10 seconds. The duration of the red light is controlled by light B, as we'll see later. On the other hand, light B is to be green for 1 minute and yellow for 10 seconds. Then it goes red. Light A turns green and the cycle repeats. At the moment, the problem may seem a bit puzzling. But once we begin our flowchart, the pieces fall into place. Our flowchart begins at the top left-hand corner. The first 5 processing blocks control light A. Assuming the entire sequence is stopped, we enter the program at the box that changes light A to green. The second process holds light A green for 2 minutes. After this interval, light A must be changed to yellow and held there for 10 seconds, as the following 2 blocks indicate. Finally, light A is changed to red by the 5th operation. Connector 1A tells us flow picks up in the bottom left-hand corner. Here we enter the light B routine that controls Side Street. Now that traffic on Main Street has a red light, it is safe to change light B to green. We hold light B green for 1 minute, then change it to yellow and hold it yellow for 10 seconds. We conclude by changing light B to red. Of course, we want this process to repeat. So we draw a flow line from the end of the light B cycle back to the beginning of the light A cycle. This is known as an unconditional branch. The program is implemented and works perfectly. Frame 49. That is, it worked perfectly until a new factory was constructed on Side Street. The factory closes at 4:30 in the afternoon, and traffic on Side Street backs up as shown at the left. A quickly implemented traffic study shows that if light B is timed for a 2-minute green between 4:30 and 5, the congestion is relieved and traffic flows smoothly, as shown on the right. However, at 5 o'clock, light timing must be shifted back to the normal cycle. Since this traffic control problem is a bit more complex than the previous one, let's define it in writing. First, we know that normal light timing works well until the factory closes at 4:30. Our traffic study shows that if light B is retimed to stay green for 2-minute intervals between 4:30 and 5, the congestion is relieved. Of course, after 5, we want the lights returned to their normal timing cycle. Also important is the fact that light A's timing cycle is never changed. It remains at 2 minutes, but we must change light B's timing cycle, 2 minutes at 4:30, and return it to 1 minute at 5 o'clock. Okay, with these points in mind, let's proceed with our flowchart. Here's the flowchart. We've combined 2 operations into one for simplicity. Also, to eliminate confusion, between 4:30 p.m. and 4:30 a.m., we've selected a 24-hour clock. Notice that 4:30 p.m. on the 24-hour clock is 16:30. 5 p.m. equals 1700. We've added 2 decision boxes to our flowchart, and they produce conditional branches. The light A routine is not altered. However, we now have 2 light B routines. The real test of a flowchart is to try it and see if it works. Our first run-through is for a time of 8 a.m. Starting at the top and following the arrows, we proceed normally through the 2-minute light A cycle. Then we reach our first decision. This is test number 1 that asks, is time greater than 1630? The answer is no. So program flow continues in the normal light B timing cycle. This means that light B is timed for a 1-minute green, which is what we want at 8 o'clock. The unconditional branch at the bottom brings us back to the top, and the process repeats. The next run-through is assuming that the time is 4:31, or 16:31 on our 24-hour clock. Arrows indicate the direction of program flow. Naturally, program flow proceeds through the light A routine. Then we reach the first decision box. The question is asked, is time greater than 1630? The answer is yes, so the yes route is taken. This leads directly to another decision box, and we encounter test 2. The question now is time greater than 1700? The answer is no. Therefore, time must be between 1630 and 1700. So we go to the 2-minute light B routine. Well, the flowchart works as defined between 1630 and 1700. But what happens after 1700? You should be able to do this one. The time is 17:01, or 5:01 p.m. Trace program flow at this time. Which light B routine does the program take? Here's the route you should have taken. Notice that test 1 is answered with a yes, since time is greater than 1630. The next decision asks, is time greater than 1700? The answer is yes, and flow returns to the 1-minute light B cycle. This takes care of times that are greater than 1700, so the flowchart works. Now, sit back and take a careful look at the flowchart. Notice that both light B routines contain identical operations. Two of the operations can be removed since they are exact duplicates. Here's the streamline flowchart. Notice that after light B is held green for 2 minutes, program flow returns to the normal timing cycle for the light B yellow and change red operations. Try it. You'll find that the end result is the same as the previous flowchart. Frame 57. Well, we made it through a pretty complex problem, didn't we? Ready for another? Here's the problem. 3 different numbers, arranged in any order, are to be sorted and rearranged so they appear in ascending, or in other words, increasing order. For example, the 3 numbers at the bottom left will be rearranged as shown on the right. Here's our flowchart. Starting at the top, we must first read in the 3 numbers. The sample numbers are shown on the right. The next operation is to subtract the second number from the first, as shown at the right. Then we ask, is the difference positive? The answer is yes. Therefore, the first number is larger than the second. Now we must interchange the first and second numbers. The results of the interchange is shown at the right. The next step is to subtract the third number, 200, from the new second number, 1600. As shown, the difference is positive, so these 2 numbers must be interchanged. Finally, we must again sample the first and second number, because they've changed. This is accomplished with another subtract operation. The difference is positive, so we must interchange the first and second numbers. The final result is shown at the bottom. The numbers are now arranged in the desired sequence, so the program stops. You'll seldom find 2 programmers that attack one problem in the same manner. Here's another flowchart for the same sort and rearrange problem. Arrows indicate flow for the 3 sample numbers. Notice that the subtract and test operations used in the previous flowchart are replaced with decision boxes. Therefore, this flowchart requires fewer operations than our previous example. Okay, we've run through a couple of different problems, so why don't you try it? We've defined the problem in this frame. When you hear the tone, stop your recorder and read the problem carefully. Then draw the flowchart and test it for different values. When you're satisfied that it works, turn on your recorder and we'll check the results. It's easier than you thought, isn't it? Let's see if your flowchart matches ours. Your flowchart may look like one of these. Don't worry about it if it doesn't. The important point is, does yours work? That's all that matters. Notice the basic difference between the two flowcharts is the decision. On the left we ask, is A greater than 5? While the flowchart on the right asks, is A less than or equal to 5? They're just different ways of asking the same question. Let's try another one. Remember, read the problem carefully before you start your flowchart. At the tone, stop your recorder and draw your flowchart. When you finish, turn on the recorder and we'll check your work. Well, this one is a bit more difficult, but it shows how much ground you've covered. Frame 63. Here are two flowcharts that solve the problem. Yours may not be like these, but remember, if it works, it's okay. The flowchart on the left uses the subtraction routine you learned earlier. The one on the right uses simpler compare statements. Both of them work. Well, there you have it. You've been through computer languages and flowcharts. You'll use your newly acquired flowcharting skills in your study of programming in Unit 4. Begin by returning to the Unit Activity Guide and follow the instructions given there. Welcome to Heathkit Continuing Education. Before you get started, we'd like to tell you how your individual learning program works. We'll begin with a brief audio-visual presentation, and then we'll take a look at lesson organization. The illustrations for all audio-visual presentations are contained in the Flipchart supplied with your lesson materials. Locate the Flipchart and set it up for viewing. You'll find that the front and back covers have fold-out flaps that form the base of the Flipchart. An interlocking tab secures the flaps. Now position the Flipchart so that the title frame Course Introduction is facing you. Flip to the next frame in sequence. This should be frame 1, as identified by the number in the lower right-hand corner. Notice that most pages have drawings on both front and back. You're only concerned with the drawings facing you. When you've gone all the way through the Flipchart in one direction, simply turn the chart around as shown on the right and go through in the reverse direction. Okay, the program works this way. When you hear this tone, flip to the next frame. Periodically, we'll identify frame numbers and keep you on track. Ready? Let's begin. Frame 2. The prerequisite for this course is an understanding of digital circuit fundamentals. The Heathkit Continuing Education Program Digital Techniques was designed specifically for this purpose. However, other training or experience may also be applicable. Practical experiments are an important part of the individual learning program, so you'll find many sprinkled throughout the course. These experiments bridge the gap between theory and practice. You'll find that we use two types of experiments: software or programming exercises and hardware experiments. All of the components needed for these experiments are included with your course materials. In addition, you'll need the Heathkit model ET-3400 Microprocessor trainer, shown on the left. Although not essential, a good general-purpose oscilloscope and volt-ohmmeter can help you analyze the circuit functions we'll be discussing. The course is structured in an easy-to-follow order. The activity guide shown here takes you through the program step by step. The course is made up of 10 units. The first 8 units cover a specific topic or lesson about microprocessors, while Units 9 and 10 contain the software and hardware experiments you'll perform. Starting at the left, we find the course introduction. That's where we're at right now. Moving to the right, we find the next segment of your studies begins with the AV presentation, Introduction to Microprocessors. Following this, you'll learn about number systems and codes in Unit 1. Next, you turn to Unit 9 and perform programming experiments 1 and 2. These exercises allow you to interact with a microprocessor trainer as you convert numbers from one number system to another. Unit 2 is next. You'll enjoy the simplified yet in-depth look at what really goes on inside a microcomputer. Then it's on to Programming Experiment 3, where you'll learn about straight-line programs. Unit 3 is a brief yet comprehensive look at computer arithmetic. Programming Experiment 4 then gives you a ringside view of the arithmetic and logic instructions at work. Unit 4 begins with an audio-visual introduction to programming. Following this, the written lesson guides you through the finer points of computer programming. Programming Experiments 5 and 6 put theory into practice as you investigate the operation of branching programs and additional instructions. In Unit 5, we begin our discussion of a typical microprocessor, the 6800. The fundamentals you learn about this microprocessor are directly transferable to other microprocessors. Programming Experiments 7 and 8 introduce new addressing modes and arithmetic operations that help you realize the full potential of your microprocessor. Unit 6 continues your study of the 6800. Programming Experiments 9 and 10 incorporate exercises on stacking operations and the use of subroutines. Your study of Unit 7 begins with an audio-visual discussion of semiconductor memories. Then you'll learn how the microprocessor interfaces with the outside world. This is a very important part of your studies because interfacing techniques permit the microprocessor to monitor and control outside activities. Interfacing experiments 1 through 4 guide you as you discover how versatile your microprocessor trainer really is. The final portion of the course begins with the audio-visual presentation, Designing with Microprocessors. Unit 8 continues your study of interfacing. Here you discover how special interface chips ease the task of microprocessor-based design. Then, interfacing experiments 5 through 9 give you practical experience as you investigate some of the more intricate problems of interfacing. Your study concludes with another audio-visual presentation that shows you how to compare microprocessors and select the right one for your application. When you complete all of the units, you'll have met the course objectives and have the knowledge and skills that you set out to obtain. No further study is required. However, there is one final step you can perform. Take the final examination contained in the final examination envelope. This examination is not mandatory, yet we urge you to take it because it's an important learning activity. Not only does it test your knowledge, but it also provides an excellent review of the material that you've covered. Another reason for taking the final exam is recognition. If you take the exam and make a passing grade, we will award you an attractive Certificate of Achievement and an appropriate number of continuing education units of credit. These CEUs are a nationally recognized method of measuring and recording your participation in an adult education program. The instructions for obtaining these credits are included in the final examination. Now set the flip chart aside for a moment as we take a closer look at the course. You can leave the flip chart set up, since we'll be returning to it shortly. At the front of the first lesson binder is a section entitled Course Objectives and Outline. We'll pause long enough for you to find this section. Okay, let's read over the objectives together. Upon completion of this course, you will be able to 1. Program a microprocessor, and 2. Interface the microprocessor with the outside world. Immediately following the objectives, we'll find the course outline. This detailed outline shows the makeup of each unit. Now open your binder to Unit 1, Number Systems and Codes. Turning to page 1-3, we find a brief introduction that sets the tone for the lesson. On page 1-4, we find the unit objectives. You should refer to these objectives often during your progress through the unit. When you can perform all of the actions described here, you are ready to take the unit examination. On the facing page, we find the Unit Activity Guide. Follow the step-by-step instructions given here, and you'll get the maximum benefit from the lesson. Now leaf through the unit. You'll find self-test reviews follow each major topic. These reviews permit you to test your retention and understanding of the subject. If you answer a question incorrectly, go back and review it until you've got it down pat. At the end of the unit, you'll find the unit examination. This test is the climax of the unit. Answer all of the questions and then check your work against the answers given. If you make a poor showing on the unit examination, be sure to review the appropriate sections of the unit before continuing. All 8 units are similar to this, with experiments and audio-visual presentations interspersed for better learning continuity. The format is structured so that it's easy to follow. Simply follow the directions in the Unit Activity Guide. Frame 1. Today, the world of electronics is in the throes of a tremendous revolution. It's a revolution that not only promises to change our daily lives by enriching the environment we live in, but also to alter our manufacturing processes. This revolution is spearheaded by a tiny electronic device called a microprocessor. Radical changes in electronics technology began as early as the 1960s with the first electronic calculators. These early model calculators were products of the transistor era that eventually resulted in the integrated circuit. The movement picked up steam in the early 70s as designers were able to cram more elements into tiny microelectronic circuits, and calculators became smaller and less expensive. Now the latest microelectronics era is upon us. It's a double-barreled thrust that's a combination of new microelectronic semiconductors and a totally new design technique. The microprocessor is a technology progression that makes the past quarter of a century look like a dry spell. It was all brought about by a relatively new technology called large-scale integration, or LSI. Using LSI, it's possible to place thousands of transistors on a tiny silicon wafer, no larger than a piece of confetti. Advances in LSI technology have made it possible to shrink the computer. In essence, this is what a microprocessor is, a tiny yet powerful computer. So powerful, in fact, that it can replace a computer that just a decade ago would have cost hundreds of thousands of dollars. Frame 6. In the past, logic design has been hardware-oriented. If you wanted a specific operation, like the adder on the left, you had the arduous task of combining many logic elements to achieve your goal. System changes were difficult to implement. You either started from scratch and redesigned the product, or if it was a minor revision, the correction could be patch-wired. Both methods were expensive and placed an unnecessary drain on engineering time and resources. For years, logic designers hypothesized, why not replace all those gates and logic elements with a stored program? The program could perform all of these functions, they reasoned. It was an interesting concept, yet at the time it was only feasible for large, expensive computers. Eventually, a convenient merging of large-scale integration and the stored program concept made the microprocessor a reality. In the microprocessor system, the program is stored in a special LSI device called a memory chip. This chip is connected to the microprocessor and supplies control instructions that cause the microprocessor to simulate the gates of conventional logic systems. Frame 11. Microprocessor-based design is a totally new concept. It's a unique mix of hardware and software that promises to revolutionize the designer's task. Hardware is greatly simplified. All functions are centered around a general-purpose microprocessor. Usually, hardware design consists of interconnection and interfacing, or matching of different LSI chips. Often a family of general-purpose chips is used in a system, producing a chip marriage that significantly reduces interfacing requirements. In microprocessor-based systems, there are less circuit elements, so naturally, less hardware design time is necessary. In essence, the brunt of microprocessor design is the development of software. Software consists of flowcharts and computer programs. These programs are written by the designer and are then loaded into special memory chips where they're stored. The program has the power to produce functions previously reserved for logic elements. Therefore, in the microprocessor-based system, memory replaces random logic by storing program sequences. As a general rule, one word of memory can replace one logic gate. It's possible to store thousands of words in only one memory chip, reducing chip count from 100 or more down to only 3 or 4. This significant reduction in hardware complexity results in reduced design time and cost, as shown here. In fact, a system that requires 1 year of design time using conventional techniques can probably be finished in only 3 months with microprocessor-based techniques. By the same token, it's less expensive. Frame 16. Since the microprocessor-based system shown on the left requires fewer components, it costs less to manufacture than the conventional logic design on the right. Fewer parts mean increased reliability, and microprocessors are no exception. They're well known for their dependability. A simple application for the microprocessor is something we call the smart scale. It's a scale that weighs packages and computes the postage required to send them to their destination. The scale then prints out the postage mailer tape. The system would look something like this. Constants such as postage rates, the geographic location of the scale, and a zip code list are programmed into memory. 2 other inputs are required. Weight is automatically calculated by the scale. The operator then types in the package destination zip code. The microprocessor computes the postage and directs the printer as it prints the postage mailer tape. But suppose the postage rates change, as they frequently do. Do you have to start from scratch and redesign the scale? Not with a microprocessor system. It's a simple matter of reprogramming memory with the new rates, a relatively painless task. Imagine the impact a change of this nature would have on a conventional logic system. Frame 21. Here we see the benefits of the microprocessor-based design when compared with the conventional design. The microprocessor reduces design and manufacturing costs and reaches the market sooner. Therefore, it captures a greater share of the market. Reliability and ease of change greatly extend product life, producing a higher profit margin. And the same general purpose microprocessor can be used for many applications. From a central temperature control system to an electronic bartender that automatically mixes drinks and calculates the price. When a microprocessor is used to perform a specific application like one of these, it is said to be dedicated. Before the advent of the microprocessor, it was a very costly proposition to dedicate a computer to one function. Today, however, such systems are inexpensive and extremely reliable. Let's look at some typical applications of dedicated microprocessors. We've all had the experience of waiting at an intersection that was controlled by a seemingly unfair traffic light. This is a problem that can easily be solved with a microprocessor controller. The microprocessor samples traffic in all directions and then adjusts light timing to keep traffic flowing smoothly. In addition, a microprocessor is so fast that one device can easily control 50 or more such intersections. We've all seen this terminal at our grocery markets and department stores. We usually call them cash registers. But in actuality, this is a new breed of register that uses a microprocessor. It's called a point-of-sale terminal. In addition to keeping an accurate account of total sales, this terminal adds up the subtotal for each purchase, computes sales tax, and then adds the two, giving the total. Finally, it prints the sales receipt. But its usefulness doesn't end here. It can also feed information such as inventory and total sales to a central computer for further processing. Probably the most exciting products to come from microprocessors will be those for the consumer, like this microwave oven. Here the microprocessor replaces buttons and knobs with an electronic keyboard and a digital display. It provides timing accuracy, precise enough to cook anything. The oven has been programmed to perform a series of operations, such as defrosting, pausing to equalize temperature, and then cooking. Design activity in other consumer products is really starting to pick up steam. Frame 26. Energy conservation is the role of this microprocessor-based system that monitors and controls heating and cooling for this skyscraper. Conservative estimates are that energy costs are reduced at least 20%. This system, because it's controlled by a microprocessor, is so inexpensive that it's even cost-efficient for small buildings. The biggest single user of the microprocessor will eventually be the automobile industry. Already, the microprocessor is being used in some cars to control engine ignition, resulting in better fuel economy and decreased exhaust emissions. Most certainly, this system will be expanded to monitor engine operation and signal a malfunction even before it occurs. The possibilities for automotive use are almost endless. This credit verification phone has as its nucleus a tiny yet powerful microprocessor. It enables merchants and bankers to check credit card business transactions in seconds. For routine transactions, the clerk merely slides in the customer's credit card. The terminal reads a magnetic stripe on the card, then checks with a central computer miles away and within seconds returns the purchase authorization. The price tags on microprocessors have decreased so rapidly that they're now starting to appear in children's toys. These toys have the capacity to become active playmates for our children. Over the next several years, smart products and machines will spread at a breathtaking rate. The microprocessor will create a host of new products so different and advanced that even our most imaginative people can't conceive of them today. Only a few years ago, a personal computer in the home was totally out of reason. Not only would it have cost hundreds of thousands of dollars, but it was so bulky and sensitive that it would have required a special environment room. Frame 31. That was before the microprocessor era. When the microprocessor is combined with a typewriter keyboard and a television-like screen, it becomes a microcomputer. This microcomputer is compact and inexpensive. Plus, it probably has as much power as the average commercial computer of only a few years ago. Today, microcomputers are usually found only in the homes of the computer hobbyist, a unique breed of hobbyist much like the amateur radio operator. In fact, we usually find they're one and the same. Nevertheless, hobby computer sales are booming and prices are dropping. In a few years, the home computer will be as commonplace as the television. The home microcomputer may first emerge in the kitchen. Here it could be used to store recipes, to help plan meals, or to keep track of perishable goods such as fruits and vegetables. In addition, it can do bookkeeping, plan budgets, or monitor investments. Here's an example of one use for the kitchen computer: the production of a weekly grocery shopping list. The housewife would type in advertisements from the newspaper and the planned recipes for the next week. The computer then checks the inventory of food items already in the cupboards against those called for in the recipes. Now the computer calculates the items you must purchase, checks these items against the prices quoted in the advertisements, and then prints out a shopping list that itemizes all purchases, neatly listed under the market with the most favorable prices. And this seemingly complex program would use only a minute fraction of the computer's potential. Assisting in the preparation of income tax returns is a simple task for the home computer. Here the computer keeps track of income tax deductions, and at tax time it lists deductions so they can easily be transferred to the income tax return. Or if it's programmed properly, the computer can even generate a completed tax form that requires nothing more than your signature. Who knows, in the very near future, it may be possible to use phone lines to connect the home computer with the IRS computer and have the tax return filed automatically. Frame 36. The totally automated home may just be over the horizon. A program now exists that can turn up your thermostat at, say, 6:30 in the morning, turn on the coffee at 6:50, run your bath at 6:53, and wake you at 7. The possibilities are limited only by the microcomputer master's imagination and programming skills. We are just now beginning to realize the potential of the computer as an educator. Computer-aided instruction, usually reserved for higher learning institutions, is now within easy reach of local school districts. And don't discount the home computer as a teaching machine. All it needs is the right program. In addition, the computer will play a large role in our leisure time by providing many hours of enjoyment with games like Star Trek, Lifeline, and chess. Yes, the computer can even become a musician. All you do is program it to play the tune you want to hear. In fact, you'll implement a program during the course of your studies that will play this same tune. Perhaps you didn't realize the part that microprocessors already play in your everyday life. They appear in products you buy, at checkout counters where you shop, control how you drive, and even have the capacity to automate your home. Is it any wonder that the microprocessor is being heralded as the new era of electronics? The economics and performance flexibility of microprocessors are right now changing the products of many industries. This era might even be called the microprocessor invasion. In any event, microprocessor-based products promise to substantially increase our quality of living. Frame 41. But to realize the potential of microprocessors and naturally become a part of this new era, you must know how this tiny microelectronic circuit can be used. This requires a knowledge of number systems, chip architecture, programming, and the related chips that turn the microprocessor into a viable system. All computers use binary numbers to represent data and to perform intricate calculations. To understand what really goes on inside a microprocessor, you've got to understand number systems. Therefore, number systems is an excellent launching point for your study of microprocessors. Begin your study with Unit 1, Number Systems and Codes. Semiconductor memories. Frame 1. By now, you're familiar with the organization of microcomputers. This simplified block diagram shows the interrelation between the MPU and memory. Memory stores information such as data and instructions, while the MPU processes information. You haven't heard much about memory at this point, so let's explore this portion of the microcomputer in more detail. One of the simplest memory elements is the D flip-flop shown here. This simple device can store 1 bit of data. Information is stored in the flip-flop like this. The procedure for loading a binary 1 is shown on the left. First, the data is placed on the D input. Then the clock pulse is applied, enabling the flip-flop. The flip-flop changes state, and the binary 1 is latched in on the output. As shown on the right, a similar process is used to store a 0. Of course, the basic flip-flop can only store 1 bit. To be a practical memory, many such flip-flops are required. Storage capacity can be expanded by paralleling flip-flops, as shown here. This array contains 4 storage elements and therefore can store 4 bits. Notice that the D inputs are tied together. Also, address lines shown on the left allow discrete selection of each flip-flop. To store data, we must first place it on the data in line. Then we enable the flip-flop by addressing it. For example, suppose we want to store a 1 in location 2. The data, in this case a 1, is placed on the data in line. Next, we enable or address flip-flop number 2 by placing a 1 on its address line in the 0 state. Since location number 2 is the only flip-flop that's enabled, it alone responds to the data and stores the binary 1. Of course, more flip-flops increase our storage capacity. Here we see 1,000 or 1,024 bits. However, notice and 32 columns. This arrangement requires 2 separate decoders, one for row selection and another for column selection. Notice, however, that each decoder only addresses 32 locations. Therefore, the decoders are further simplified, the real advantage of this memory array. Here's how this memory is addressed. Suppose the desired address is location 528. The binary representation for this number is placed on address lines A0 through A9. The lower order addresses A0 through A4. Go to the row select decoder and row 16 is enabled. At the same instant, addresses A5 through A9 are fed to the column select decoder. This enables column 16. The memory cell located at the intersection of the row and column lines is therefore enabled. In this case, it's address 528, and the bit of data stored here is placed on the data bus. To obtain a more usable memory with, say, an 8-bit word, 8 of these chips are placed in parallel. The row and column address lines are also paralleled. The data lines are then brought out, each line representing 1 bit. Combined in this manner, we have an 8-bit by 1K memory array. Before we go any further, let's nail down a term that you'll hear frequently in memory discussions. This term is K. In any other situation, 1K means 1,000. But in memory, it means 1,024. This results from the binary number system, where the power of 2 closest to 1,000 is 2 to the 10th, or 1,024. Therefore, 1K is actually 1,024 bits. Likewise, 4K is 4,096 bits, and so forth. Okay, we've talked about simple memory systems and how they're addressed. Now let's look at 2 categories of semiconductor memory. These are the RAM and the ROM. RAM stands for Random Access Memory, while ROM represents read-only memory. Let's examine each of these in more detail. Basically, here's how random access works. Memory locations are arranged in a matrix. The example here has 16 rows or addresses. Each row contains an 8-bit word. 4 address lines feed the decoder, which can select any one of 16 discrete locations. In this example, the address shown on the left is a binary 2, and the arrow shows that row 2 is enabled. The 8-bit word stored at this location is fed to the data bus. This brings up another memory term called access time. Access time is the period required to obtain data from memory. It's usually measured in micro or nanoseconds. The important point about random access memory is that data can be accessed in a fixed amount of time, no matter where it's stored. For example, data at address 15 can be accessed just as fast as data at address 0. Actually, we find that both RAM and ROM are random access type memories. Essentially, they are arranged the same, each containing an address decoder and a memory matrix. Let's look at the real difference between RAM and ROM. Frame 16. When you see RAM, think read-write memory, because that's really what it means. Information stored in memory can be read out by the read operation on the left, or data can be stored or written into memory by the write operation shown at the right. Therefore, the RAM is changeable. We can store information in RAM and then read it out, or we can change the contents of RAM by simply writing over what's stored there. Essentially, RAM memory can be used like a scratch pad. RAMs can be divided into 2 categories, static and dynamic. These classifications result from the type of memory cells used in each device. The static cell on the left is the basic flip-flop discussed earlier. The dynamic cell on the right is an ingenious use of the capacitor to store data. Here we see the schematic for one static cell. The memory array contains many of these, all interconnected through the bit and row lines. Notice that 6 transistors are required for one static flip-flop. The characteristics of the static RAM are listed on the right. First, the static RAM is bistable, meaning it has 2 stable states. When data is stored in the flip-flop, it is effectively latched in. The static RAM requires only one power supply. It's also easy to use, requiring few peripherals, if any. Access time is typically 0.5 to 1 microsecond. Operating power for the static device is approximately 400 microwatts per bit. Finally, as of this recording, 4K bits can be stored on a single chip. Storage capacity brings to mind another term you'll hear frequently. It's called packing density, and refers to just how many memory cells can be crammed into a given chip. Semiconductor memories are fabricated using the same large-scale integration technology that's employed for microprocessors. Here we see two enlarged photographs of memory chips. The actual chip size is about 140 mils on a side. On the left is a 1K static RAM, while the chip on the right is a 4K dynamic RAM. Although the chips are virtually the same size, the dynamic RAM has 4 times the capacity of the static. Therefore, the dynamic RAM has higher packing density. This difference in packing density is evident when we look at the makeup of a dynamic cell. The dynamic cell is simplicity, almost to an extreme, as it's comprised of one transistor and one storage capacitor. Frame 21. Here we see the real advantage of high packing density. One seemingly complex static cell is shown on the left. On the right, we see that in the same physical area, we can place 4 dynamic cells. Here are the advantages that are reaped from high packing density. As you've seen, more memory can be placed in a given chip area. This reduces the cost per bit. Fewer transistors are required for a given storage cell, so less power is consumed. This makes the device cooler running. Finally, the device has a very fast access time because there are fewer transistors to turn on or off. Of course, there is a price to pay for the higher packing density of the dynamic RAM. The price in this instance is the fact that the basic storage device is a capacitor, and all capacitors allow some leakage current. Therefore, the capacitor will allow a charge to leak off, and the stored data will be lost. For the dynamic RAM to be an effective storage device, the charge on the capacitors must be periodically restored. This is accomplished with a refresh circuit. Some refresh requirements are quite stringent, resulting in complex circuit designs. However, advances have been made in this area, and today, some dynamic RAMs incorporate the majority of the refresh circuitry right on the chip. Typical characteristics of the dynamic RAM are shown here. They begin with the advantageous low cost per bit. Access time is typically 200 to 400 nanoseconds, and operating power is less than 110 microwatts per bit. Storage capacity is up to 16 kbits. The disadvantages of the dynamic RAM are that it may require 3 separate power supplies and extensive refresh support circuitry. Nevertheless, it's an excellent device for large systems that require huge memory capacities. Frame 26. Let's compare the characteristics of static and dynamic RAMs. The first category for comparison is the all-important cost per bit. The dynamic gets a check here because it's less expensive. The dynamic RAM receives another check mark because of its superior access time. Also, the dynamic wins in the categories of power dissipation and packing density. At this point, it appears that the dynamic RAM is far superior, and where performance is concerned, this is the case. However, one other consideration that's extremely important is ease of use. Here the static RAM wins hands down, since it only requires one power supply and doesn't need external refresh circuitry. In some cases, ease of use is the determining factor for selection. Really, the only problem with RAMs is that they are volatile. By this, we don't mean that they're flammable. Instead, volatility in memory terms means that if power is removed, even for an instant, all memory is lost. Therefore, for the RAM to retain data, power must be maintained. Of course, a standby power supply, such as the battery shown here, can prevent loss of RAM memory during temporary power failures. But this backup system has its problems. For example, it isn't entirely reliable. In addition, the battery can only supply a limited amount of power. Although the standby power supply is frequently used, it's far from foolproof. Fortunately, the other type of semiconductor memory, the ROM, is non-volatile. ROMs retain data even with power removed. Here we see the schematic for a simplified ROM array. Diodes are used as the basic storage device. As shown at the top, when a diode is connected to the bit line, a binary 1 is stored. An open connection indicates a binary 0. Frame 31. Data is read out by simply addressing a word line. This places a high on the addressed line, in this case, word line 1. Now remember, a connection is a 1, and an open is a 0. At the points where the diode is connected, current flows through the bit line resistor, up the bit line and through the diode. The corresponding 1, therefore, appears on the bit line. On the other hand, an open connection doesn't allow current flow, and the corresponding bit line indicates a 0. ROMs, the unchangeables. In normal use, the ROM can only be read from, never written into. Basically, there are three types of ROMs: the mask ROM, the PROM, which stands for Programmable ROM, and the EROM, an electrically alterable ROM. You may hear the EROM referred to as an EPROM, but no matter, they're one and the same. Let's look at each of these in more detail. The masked ROM is programmed during manufacture. The chip is fabricated using the same photomasking and etching technique employed for other integrated circuits. First, diodes are formed on a wafer by photoetching. Then the program mask is placed over the wafer and the etching process is repeated. Actually, the mask programs the ROM. To store a 1 in a location, the mask makes a connection. To program a 0, the connection is left open. The programming mask is developed by the chip manufacturer using a program supplied by the user. Of course, a setup or tooling fee is charged for this service. Mask ROMs are inexpensive when they're mass-produced. Although the masking fee may be quite high, it usually only amounts to a few pennies when spread out over thousands of identical ROMs. However, the mask ROM does have its drawbacks. To alter a program, you've got to replace the ROM. Naturally, this means another masking fee and another run of brand new chips. Also, there are situations where only 1 or 2 ROMs are needed. The mask ROM is far too expensive for these limited quantity applications. Fortunately, there is a ROM that's excellent for small quantity use. It's the PROM, a field programmable read-only memory. Frame 36. Here we see a simple PROM array. A fuse is placed in series with each diode. The fuse makes the PROM programmable. The PROM is simple to program. The drawing at the left shows how it's done. First, the desired word is addressed. Then the complement of the data to be stored is applied to the bit lines. A binary 1 forces a large current through the fuse and diode, opening the fuse. No current is produced by the binary 0, and the fuse remains intact. The program PROM is shown on the right. A blown fuse represents a 0, while an intact fuse represents a 1. Therefore, the PROM can be written into only once during programming. From then on, it's strictly a read-only memory. Here we see the PROM programmer, called a PROM burner. The PROM is plugged into a socket, and the program is entered with the keyboard. Electrical impulses blow the fuses, burning the program into the PROM. Of course, there are applications where the stored program must periodically be altered, but where non-volatility is essential. For these applications, the electrically alterable ROM, called an EROM, fills the bill. Here we see a 4-cell portion of an EROM. Each cell contains the standard MOS transistor and a floating gate MOS device. The floating gate transistor is the storage device. The cell is programmed by injecting a high-energy charge into the floating gate. An insulating oxide coat forms around the gate and holds the charge in place. The absence or presence of charge indicates stored data. The EROM is programmed with the PROM burner shown on the left. The EROM is erased by exposure to a concentrated ultraviolet light, as shown on the right. This discharges all gates. The EROM is then reprogrammed. Frame 41. Here we see how memory is arranged in a hypothetical microcomputer. The memory shown in the center contains both ROM and RAM devices. We have a 2K by 8 section of ROM and a 512 by 8 section of RAM. This gives us a memory with an 8-bit word. The non-volatile ROM stores the microprocessor control instructions, called the monitor program. RAM is the temporary storage section where user programs and data are stored. So when you load a program into the microcomputer, it's stored in RAM. A sound knowledge of how the microprocessor communicates or interfaces with memory is necessary to really understand how the microcomputer works. You'll learn more about interfacing in this unit. So continue your study by returning to the unit activity guide and following the instructions given there. Designing with microprocessors. Frame 1. A microprocessor-based design offers many tangible benefits over conventional logic designs. The advantages are listed here. They begin with a significant reduction in development time and cost. Manufacturing costs are decreased since there are fewer components to assemble. This lower part count contributes to increased product reliability. From the marketing standpoint, custom features are easily added, usually with simple program modifications. Microprocessors give us a big edge in the marketplace, as shown here. When compared, we see that products using microprocessors reach the market sooner than similar conventionally designed products. Therefore, the microprocessor-based system garners a larger share of the market and has a longer product life. Of course, there comes a time when you have to decide whether to use or not to use the microprocessor. Here are a couple of general guidelines. First, would a conventional design require more than 30 ICs? Or are frequent system changes expected? Does your system require arithmetic functions? If you answer yes to any of these, a microprocessor-based system is probably warranted. Okay, you've got all the tools needed to design with microprocessors, and you know you can do it. But where do you start? How do you take your knowledge of microprocessors and programming and funnel it into a design of the microprocessor-based system? You begin just like you would for a conventional design. You specify the functions. Be sure to state exactly what you want the system to do. Careful planning at this point can eliminate those last-minute changes that are so time-consuming. Frame 6. The next step is to draw a block diagram of the system as you see it. Basically, you're looking at hardware requirements. Of course, these may change when you begin to realize what you can do with software. All you're trying to do is lay out the basic hardware requirements. Next, flowchart system operation. This places the defined functions in sequential order, a really important step. As you flowchart the system, you'll probably find that some hardware revisions are necessary. If so, go back and check the block diagram. Then modify it to handle any problems that surface during the flowchart sequence. At this point, you begin to make trade-offs between hardware and software. Most problems can be handled with software, but at times hardware is the only way to go. The next step is to break the system flowchart down into subroutines. Each major step is divided into one or many subroutines depending on complexity. Now, when all the subroutines have been flowcharted, you're ready to write the main control program. You do this by writing individual programs for each subroutine. These small programs are then combined to form the control or monitor program. Notice that the subprograms, as we call them, are written in assembly language. Frame 11. Now we're ready to assemble the subprograms to form the main control program. Since the subprograms are written in assembly language, they must be loaded into the computer that contains an assembler program. The assembly process combines the subprograms forming the control program. Then the program is edited and debugged. Finally, the source program is produced, in this case on paper tape. The next step is to simulate the program. This process begins with loading the source program into a simulator. The simulator contains a microprocessor and an associated family of memory devices like those used in your system. Essentially, the simulator is a mirror image of the hardware that you'll use with your program. In other words, it simulates your system. If the program works on the simulator, you can be pretty confident it will work on your finished design. Now the control program is loaded into PROM. Finally, we're ready to build a prototype model of our system. But since we've already simulated the system, we're confident that it will work. Then we plug the program PROMs into the prototype and proceed to test and evaluate the design. Now it's a simple matter of clearing up any glitches we might have introduced when we built the prototype. Frame 16. Well, now you can probably see some of the real advantages of microprocessor-based design. To further reinforce the design approach, let's look at a sample problem. For our example, we've selected a weather station, an application that's well within the capabilities of the microprocessor. Here are our system specifications. We want the weather station to sequentially display temperature in degrees Fahrenheit, from minus 100 degrees up to plus 127 degrees. Wind speed in miles per hour from 0 to 99, and wind chill in degrees Fahrenheit from plus 70 degrees to minus 150 degrees. Also, when a push button is depressed, we want to display either the maximum temperature, minimum temperature, or maximum wind speed that occurs in a 24-hour period. Now, with these specifications in mind, let's move on to the next section of the design process, that of developing the block diagram. Although there is no cut-and-dry procedure for this stage of design, here are some points we should consider, such as which microprocessor are we going to use? How much memory do we need? Which display technique is the most economical? What sensing devices are best? And exactly what is the format of the input data? Here are a few of the factors that figured into our microprocessor selection. First, an 8-bit data word was essential to handle the information from our temperature sensor. Design is simplified if the microprocessor has a family of hang-on chips, such as ROMs and RAMs, because then we don't have to concern ourselves with chip interface. A good comprehensive instruction set simplifies programming, and operation from a single power supply will reduce design problems that usually surface in this critical section. How much memory do we need? Well, experience is the best guide here, and we estimate that we need 512 bytes of ROM for the control program and less than 128 bytes of RAM for temporary storage and scratchpad. But we could just as easily wait until the program is assembled before we nail this down. Frame 21. For the display, we've selected 6 7-segment LEDs. While we're talking about displays, we might as well confirm the format for each. As shown in the center, temperatures below 0 will be indicated with a minus sign, while those above 0 will be displayed as shown on the right. Wind speed will be formatted as shown on the bottom left in miles per hour. Since the 7-segment display can't form an M, we'll use the 2 center displays to form a lowercase m. The wind chill format is shown in the lower right-hand corner, and to eliminate confusion with the temperature display, we place a C in the leftmost digit. The input devices we've selected are the thermistor for temperature indications and a wind cup type transmitter for wind speed. Of course, both sensors produce analog data, which must be changed to digital. This conversion is certainly within the capabilities of the microprocessor, but for the sake of simplicity, we'll make the conversion with analog to digital converters. Here's a block diagram for our system. Starting at the left, we find the power supply, our clock, the microprocessor, and in the center, our memory. The LED display is comprised of a data latch and the LEDs. On the right, we see the analog to digital converters for our 2 inputs, temperature and wind. The entire system, as we see it now, contains only 8 blocks. The system flowchart is next, and we begin ours by initializing the system. Then we go immediately to a display temperature routine. This will latch the present temperature into the display, and at this point, our microprocessor goes into a 2-second delay routine. After the delay, flow continues through the wind speed display routine, followed by another delay, then the wind chill display routine, and finally another 2-second delay. Then we branch back to the temperature routine and the cycle repeats. For the push-button functions like high temperature, we've selected hardware interrupts. We'll examine these functions a little later. Now, let's begin the process of breaking the system flowchart into individual subroutines. Some subroutines are evident just from examination of the system flowchart. You've probably already noticed one. The system flowchart on the left shows that the 2-second delay routine is repeated 3 times in one flowchart cycle. Therefore, the 2-second delay is an excellent candidate for a subroutine. As shown at the right, we've modified the system flowchart and inserted a delay subroutine. Each time the delay connector is encountered, the program jumps to the subroutine. Upon completion of the delay, flow returns to the main program. Frame 26. The 2-second delay is a classic example of how easily hardware can be replaced with software. Remember, the microprocessor requires a fixed amount of time to complete one cycle. In our microprocessor, 1 MPU cycle is equal to 2 microseconds. Also recall that certain processes take longer than others. For example, the DEX, or Decrement Index Register instruction, requires 4 MPU cycles, or 8 microseconds. One no-op instruction uses 2 MPU cycles. Therefore, 4 no-ops will require 16 microseconds. The branch if not equal 0, or BNE instruction, needs 4 cycles or 8 microseconds. Therefore, one loop through the delay subroutine requires 32 microseconds. Now, keeping these points in mind, let's examine how this subroutine produces a 2-second delay. At the left, we see our delay subroutine on the first loop. The first instruction is to load the index register with zeros. Then we decrement the index register with a DEX instruction. Now the index register contains all ones, or the binary equivalent of 65,535. 4 no-ops are next, and they are included simply to slow down the process. Now we test to see if the index register is 0. It's not, so the program loops back and runs through again. Actually, this process continues for 65,536 loops. On the final loop, shown at the right, the BNE test finds a 0, and we return to the main program. Since each loop requires 32 microseconds, the total delay is just over 2 seconds. Of course, by manipulation of the no-ops, we could fine-tune the delay, but this is close enough for our purpose. This concludes instructions on Side A. Fast forward your tape machine to the end of the tape, turn the cassette over, and continue on Side B. The key to an effective program is to attack tiny portions of the overall program. In other words, divide and conquer. Therefore, we can divide the system flowchart into many subroutines. Then we attack each subroutine separately. As individual problems surface, subroutines can be written to cope with them. All of the subroutines will then be combined to form the control program. As an example, let's look at how we handle one subroutine. Here's the flowchart for the temperature subroutine. Following the flow, we see that first we read the temperature. Then we test to see if the new temperature is greater than the previous high temperature, H-temp. If the answer is yes, then we have a new high temperature and we store it in location H-temp for further processing. A similar test is used to determine if the present temperature is less than the previous low temperature L-temp. Next, we display the temperature and then exit to the delay routine. The labels that we assign to specific memory locations in this early phase will be a tremendous asset later. Once we begin to flowchart the individual subroutines, we discover that most routines require a display block, as shown at the left. Therefore, we can handle this complicated task by writing a separate display subroutine. As shown at the right, when we wish to display data, in this case temperature, we move this data to a memory location called display, and then jump to a display subroutine. Notice that since a delay always occurs after a display, we'll chain these two subroutines together. At this point, the program is coming together pretty well, and we'll continue to flowchart all of our subroutines. Frame 31. You'll remember that our specifications include displays of either the highest or lowest temperature, or the highest wind speed that occurs in a 24-hour period. In other words, when one of three switches is pushed, we want to stop the main program and branch to a special program that will display the desired information. Let's look at this area of the program. We can implement this branching function with one of two methods: the program control method on the left, or the hardware interrupt on the right. Using program control, we test for a switch closure once each loop. If a switch is closed, we branch to a service switch routine that displays the called data. However, because delays are incorporated in our display program, it takes approximately 6 seconds to complete one loop. It's possible that a delay of 6 seconds may occur between the moment the switch is pushed and the instant the desired information appears. This time lapse is far too long to be practical. On the other hand, the hardware interrupt will stop the program immediately, giving us an instantaneous display. Therefore, the hardware interrupt is the option we've selected. Here's the circuit that will initiate the interrupt. Notice that interrupt switches connect to two places, a data buffer and an OR gate. A switch closure will satisfy the OR gate and initiate the interrupt. The microprocessor then outputs an address that enables the buffer. Data that corresponds to the switch closure is placed on the data bus. This allows the microprocessor to identify the switch and then jump to the corresponding routine. Here's the flowchart for our interrupt service routine. First, we enable the interrupt data buffer. Then we poll the data line to locate the close switch. A 1 on a specific data line branches the program to the appropriate subroutine. After the subroutine is executed, we return to the main program and pick up flow at the point of the interrupt. Naturally, we have to write 3 additional subroutines. One for display of high temperature, one for low temperature, and another for high wind speed. Once we've flowcharted all of the subroutines, it's time to begin putting it all together. This is the programming phase, where we write a subprogram for each subroutine. Here we see the subprogram for the temperature subroutine. Notice that the program is written in assembly language. Labels represent memory locations and subroutines. There's no need to compute relative addresses. The assembler does it for us. Frame 36. Now it's time to combine all of the subprograms into the complete program. In other words, the program is to be assembled. Recall that during assembly, an assembler program is stored in the computer. Now we load our subprograms into the computer. Here we use a typewriter terminal for entry. The computer checks for syntax errors and then assembles the program, inserting opcodes and operands. Finally, the finished assembled program is printed out and simultaneously stored on magnetic tape. The next step is to simulate the program to make sure it works with the selected microprocessor. Simulation is divided into 2 phases: software simulation, shown here, and hardware simulation. We simulate software like this. First, the program is loaded into the simulator and stored in RAM memory, as shown at the left. The simulator contains a microprocessor, just like the one used in the system we're designing. The simulator then processes the program and prints out a simulation listing of the program's operation. As shown on the right, the simulation listing shows step by step the contents of the program counter, the index register, and accumulators. Now we check the listing to make sure the program works as designed. Well, we've gone this far, but we still haven't touched the hardware. Yet we're sure that our program works. Now let's clean up those problems of interfacing with the outside world. This is the hardware simulation phase. To do this, we add an I/O board to the simulator, and then we breadboard all of the peripheral circuitry like the display and the wind and temperature inputs. Then we simulate all inputs and check out the program. Now we're sure the system works in all respects. Now we take the program listing and program our proms. This can be accomplished manually as shown here, or if the program is on paper tape, automatically. The final step is to build our prototype and then test and evaluate the system. The PROM stores the control program. If no new problems are introduced, and they shouldn't be, the system will work as specified. Designing with microprocessors is a whole new ballgame, isn't it? As you can see, you're almost finished with the entire design before you even build a prototype. And if you follow the procedure, you'll design new, more reliable products in a much shorter time than is possible with conventional logic systems. And what about system changes? The microprocessor-based design gives you versatility like you've never seen before. Let's say we want to change the system so it will display temperature in degrees centigrade, or perhaps we want to add a time display. It's usually just a simple matter of rewriting a portion of the program and replacing the proms. Now, don't get the impression that your first microprocessor-based design is going to be a snap. Odds are it won't. But as you gain experience, you'll find it gets easier and easier. The proper mix of software and hardware makes an almost unbeatable combination. Now continue your study of microprocessors by returning to the Unit Activity Guide and following the instructions given there. Comparing microprocessors. Frame 1. There are many microprocessors on the market today, but the selection of the right microprocessor for the job is far too important to be left to chance. Comparing microprocessors is like comparing hand tools. The selection depends to a large degree on the application and personal preference. No matter how differently microprocessors are structured, we usually find similarities. Most microprocessors contain these basic elements, although the names may change. Yet each microprocessor is unique. For example, the microprocessor on the left has a 16-bit index register and 2 accumulators, while the one on the right has 6 general-purpose 8-bit registers, but only 1 accumulator. These subtle differences must be examined carefully during the selection process, for they can indicate programming problems or solutions. Microprocessor analysis begins here, the comparison of manufacturers' data sheets. Data sheets tell you a lot about the individual devices, and you may begin to cull out the misfits at this early phase. Frame 6. Here are a few guidelines you can use for comparison. We usually begin with word size, addressing modes, the maximum address, and input-output capability. How many internal registers does the microprocessor contain? How extensive is the instruction set? Execution speed is important, along with the interrupt structure. From the hardware standpoint, interface complexity and supply voltage requirements are of the utmost importance. And finally, don't forget the importance of manufacturers' hardware and software support. Good support can significantly reduce design time. Let's look at each of these in more detail. Word size is usually the first feature that's considered. It's also the means we use to classify microprocessors. Word size is important from the standpoint of resolution, computational accuracy, and programming ease. For example, the 8-bit microprocessor on the left processes an 8-bit data word. The 4-bit unit on the right can also process an 8-bit word, but it requires 2 data bursts. Using the 4-bit microprocessor for 8-bit data usually isn't time efficient and most certainly complicates programming. The number of addressing modes offered by the microprocessor is very important. Here we see 5 of the most commonly used addressing modes. As a general rule, more addressing modes means more potential power. A word of caution here, however. Some of the addressing techniques pointed out in the data sheets may be of little or no use, or it may simply be a rehash of a mode that's inherent in other microprocessors. The amount of memory that's directly addressable is known as the microprocessor's address capability. The microprocessor on the left has a 16-bit address bus and can directly access 65K of memory. The 4-bitter on the right has a combination address data bus. However, it can address 4K of memory by applying 3 bursts of 4-bit multiplexed address information. The disadvantage of the multiplexing technique is obvious, since more time is required to address a memory location. Since the microprocessor takes data from the outside world, processes it, and possibly returns the result, the input-output structure is very important. Basically, there are 2 types of I/O structures, the dedicated on the left and memory mapped on the right. The dedicated I/O system has a limited number of ports and requires special I/O instructions. On the other hand, the memory mapped method treats input-output data just like memory. Usually, this is more versatile. An added plus, any portion of memory can be allocated to input-output. Frame 11. All microprocessors have the standard registers, such as a program counter and an accumulator. What we're looking for here are extra user-accessible internal registers, like extra accumulators, index, and general-purpose registers. These additional registers can mean programming economy. Another general rule: more registers make a more flexible microprocessor. When we compare the registers of microprocessors A and B, it appears that A is superior, since it has 3 16-bit general-purpose registers, compared to B's extra accumulator and index register. However, don't make a hasty judgment. Be sure to examine the instruction set, because here's where we find out how flexible the registers really are. The microprocessor's instruction set is as important as any other selection criteria. It should be well organized so it's easy to learn, powerful so a few instructions can perform complex tasks. If it's memory efficient, complex routines will only use a small amount of memory. And remember, memory is money. Naturally, how time efficient the instruction set is reflected in how few memory cycles are necessary to complete a given task. Execution speed is also important. In the past, clock frequency has been the standard, assuming that the faster the clock, the faster the execution speed. However, this can be misleading as shown here. The clock frequency of microprocessor A is twice that of B, so naturally A appears faster. But when we compare how long it will take to add the contents of 2 registers, we find this requires 2 microseconds in both A and B. Therefore, today, the most popular estimate of computational speed is the register-to-register addition time. 3 basic interrupt structures are shown here. The simple single-line interrupt on the left ties all interrupts to a common interrupt line. The microprocessor must poll to locate the initiating interrupt. The multi-level interrupt on the right has more than one hardware interrupt line. The interrupt is identified immediately, without polling. The vectored interrupt at the bottom is the fastest. It not only requests service, but automatically branches the program to an interrupt service routine. Frequently, we'll find these interrupts combined in one microprocessor. Interfacing with the outside world is a major problem, no matter which microprocessor you select. Therefore, as a designer, you don't want to be bothered by bus interfacing problems inside the system, like having to buffer the address and data buses. There's strength in the microprocessor family, since these chips can usually be connected directly without additional buffering. Also look for TTL compatible voltage levels. Frame 16. The economy of one power supply is obvious. Multiple supplies mean more power supply design time. But be careful that the support chips, such as memory and peripherals, also use the same supply. This is part of the beauty of family devices. They are compatible. Manufacturer's hardware support is an important consideration, because this is a measure of the manufacturer's commitment to servicing the user's needs. Look for a readily available design development system and a simulator or emulator. As you know, these are the real time savers in the design of microprocessor-based systems. And don't forget software support. This includes documentation, such as programming manuals, application notes, and other technical literature. Also included under the umbrella of software are special programs for assembly, simulation, diagnostics, and debugging of your monitor programs. When you've gone through the microprocessor datasheets and compared the different features, you'll find that you've narrowed the field considerably. Now it's time to obtain additional information on the microprocessors still in the running. This information can be ordered directly from the manufacturer or from a local distributor. You might even have a representative from the company in for a chat. Now, armed with this information, carefully examine the architecture of each microprocessor. You can use the manufacturer's standard drawing, or you may find it helpful to redraw the diagram so it's in the form you're familiar with. Look at these particular areas. the register resources, the memory resources, and the input-output structure. Try to get comfortable with the hardware. Frame 21. Now that you know the hardware, carefully evaluate the instruction set. What you're trying to determine is its efficiency. Examine these 4 instruction groups: data transfer, arithmetic logic, control transfers like branches and jumps, and machine control instructions like no-ops and halt. At this point, you should have narrowed the field to no more than 2 microprocessors. To select the winner, you'll use a special program called a benchmark. You must write a benchmark for each microprocessor. The benchmark program usually consists of from 100 to 200 instructions and should resemble the application for which you'll use the microprocessor. Both programs must do identical operations. A spin-off of the benchmark program is that you get first-hand experience using the instruction set, and you begin to get a feel for how easy or complicated the set is. The next step is to compute the instruction execution time for each program. You do this by making up a chart that shows the instruction time for each operation and the frequency of execution, which means how many times the instruction is performed in the program. The next step is to calculate the typical instruction time in microseconds, as shown in the left-hand column. To do this, simply multiply the frequency of execution and the instruction time. Now add them all up, and you've got the total instruction execution speed. For this benchmark program, Microprocessor A is the fastest. And for this application, Microprocessor A would be the choice. However, for other applications, B may be faster. Therefore, it's extremely important that the benchmark program reflect the job for which the microprocessor is intended. As you've seen, microprocessor selection is too important to leave to chance. If you follow these guidelines, you'll end up with a microprocessor that suits your application. Sure, it takes a little more time to do it the right way, but the time you spend here will be returned tenfold when you actually get into the design phase. Now let's look at a few of the microprocessors that you have to choose from. The first group we'll look at is the 4-bit microprocessor. Although there are many 4-bitters, we'll confine our discussion to 2 of the most popular, the 4040 and the PPS-4. Frame 26. Here we see the block diagram for the 4040. The important hardware features include an address stack that has 7 levels, each 12 bits wide. This permits 7 levels of subroutine nesting. As shown on the right, it also contains index registers that can be used as either 12 8-bit address registers or as 24 4-bit storage locations. Some of the features of the 4040 are shown at the right. It can directly address 4K words. The typical register-to-register addition time is 10.8 microseconds. It also has a vectored interrupt capability, a 60 instruction set, and decimal arithmetic capability. The PPS-4 has an 8-bit instruction data bus and a separate 12-bit address bus. As indicated by the arrows at the left, an internal stack made up of registers SA and SB is provided. In addition, the stack can be expanded to RAM. Control flip-flops FF1 and FF2 provide conditional branching. The arrow at the right points out that register X is for temporary storage of either the accumulator or BM register. The important features are highlighted by check marks. They include a 5 microsecond instruction time, direct addressing of 16 input-output circuits, a 50 instruction set, and a single-level interrupt that can be expanded to 15 levels. The 8-bit microprocessor is by far the most popular. We'll discuss 7 of these chips. You're thoroughly familiar with the architecture of the 6800, so we'll just highlight some of the features. The 6800 has 6 addressing modes, a 72 instruction set, an excellent 2 microsecond register-to-register addition time, a maskable vector interrupt structure, plus a non-maskable interrupt, requires only 1 power supply, and can drive up to 10 family chips without bus extenders. Here we see the architecture of the 8080A. As shown, the 8080A has only 1 accumulator, but it has 6 8-bit scratchpad registers that can be used as such, or as 3 16-bit registers. The temporary register pair W and Z are not accessible to the programmer. Important features are checked. They include 4 addressing modes, a 78 instruction set, 2 microsecond add time, plus 256 input-output ports. Frame 31. The Z80 shown here is an enhancement of the 8080 microprocessor. The major hardware differences are illustrated by the number of internal registers shown at the bottom. The shaded areas represent those registers found in the 8080. Notice that the main registers are duplicated in a set of alternate registers. The Z80 also has 4 additional special purpose registers, an interrupt vector register, a special dynamic RAM refresh register that provides all of the necessary refresh logic for external dynamic RAM, and finally, 2 16-bit index registers. Important features are checked on the right. They include 10 addressing modes and a whopping 158 instructions. Of course, the Z80 is software compatible with the 8080 and has a 1.6 microsecond register add time. We don't want to overlook the built-in refresh circuitry. The F8 is an input-output oriented microprocessor, as evidenced by 2 8-bit I/O ports on the left. It also has an onboard clock circuit. The F8 contains 64 internal registers to serve as a workspace. For simple applications, RAM may not be required. Simply use these 64 registers. Notice that the program counter and stack register aren't on the microprocessor. Instead, these registers are located on a special ROM. Important features are 8 addressing modes, 60 instructions, and a 2 microsecond add time. Here we see the unique features of the 2650 microprocessor. Starting at the left, we find an 8-level stack register. At the bottom left, we see an address adder that calculates relative and indexed addresses. Probably the most unique feature is found in the 7 general-purpose registers shown in the center. Register 0 is thought of as an accumulator. The remaining secondary registers form 2 3-register banks. Points of interest are that the 2650 can only address 32K bytes. This is the result of the program counter being only 15 bits wide. There are 6 addressing modes and 72 instructions. It takes 4.8 microseconds to add registers, but it only requires a single 5-volt power supply. There are many models of the so-called 6500 microprocessor. Some contain onboard clocks, and they come in 2 package sizes, 40-pin and 28-pin. Here we see the 6502 chip, a 40-pin package. As pointed out at the bottom right, the 6502 has the onboard clock. Although the 6500 series is frequently thought of as an enhanced 6800, careful examination of the architecture disproves this. Notice that it has only 1 accumulator, and as shown at the top, the index register is broken into 2 8-bit registers. Also, the 6502 has a stack pointer that's only 8 bits wide. Important features are 13 addressing modes and 56 instructions. The 1 microsecond register addition time can be very important in high-speed applications. We'll conclude our discussion of 8-bit microprocessors with the CDP-1802, affectionately called the COSMAC. Unique hardware appointments are 16 general-purpose registers that are 16 bits long. Any one of these registers can be designated as the program counter by the P register. The N, P, and X registers point to a register using the 4-bit register select line. The D register functions as the primary accumulator. Distinctive features are pointed out on the right. The chip is fabricated with CMOS technology, providing high noise immunity and low power drain. The COSMAC has 4 addressing modes and 91 instructions. However, the register-to-register add time is only 6 microseconds. Frame 36. There aren't very many 12-bit microprocessors. However, the 6100 is very popular. Its popularity probably stems from the fact that it's a 12-bit microprocessor that's software compatible with the PDP-8, the world's most popular mini-computer. The 6100 architecture is straightforward, and the main registers are 12 bits wide. Important features include its software compatibility with the PDP-8. It only addresses 4K words, but each word is 12 bits. This is usually more than enough memory for most programs. Its instruction set contains 69 instructions. Also, the chip is fabricated using CMOS technology, which has the advantages already discussed. As of this recording, there are several 16-bit microprocessors on the market. We'll discuss 2 of the most popular. The IPC-16 shown here is referred to as the PACE, an acronym for Processing and Control Element. As shown by the shaded blocks, the PACE has 4 16-bit accumulators. Accumulator 0 is thought of as the primary accumulator, and accumulator 1 as the secondary. Accumulators 2 and 3 are used as secondary accumulators and index registers. As shown at the bottom left, an on-chip stack is provided that's 16 bits wide and 10 words deep. Important features are checked to the right. PACE can directly address 65K words, and each word is 16 bits. It has a 45 instruction set. The 8 microsecond register add time appears somewhat disappointing, but remember, these registers are 16 bits wide, so the PACE addition is comparable, if not quicker, than the fast 8-bitters. The TMS 9900, shown here, is a popular 16-bitter that approaches the mini-computer performance level. Notice that the MPU only contains 3 user-accessible registers. The workspace register is the most unique and powerful programming feature of this chip. This register identifies the first of 16 general-purpose registers located in RAM. These RAM registers can be used as either accumulators, index registers, for temporary storage, or for storage buffers. A very minor drawback to this arrangement is that the system cannot operate without a separate RAM chip. However, this architecture gives us the unique feature of variable hardware and software, making the 64 instructions extremely powerful. Other big pluses are the built-in multiply and divide capabilities. Frame 41. As you can see, there are many microprocessors to choose from. The final choice usually depends on the application. With your knowledge of microprocessors and programming, you'll be able to select the chip that suits your needs and simplifies design. Well, you've come a long way toward realizing the potential that microprocessors offer. But don't stop now. You'll find that the knowledge you've acquired can be channeled toward learning other microprocessors and mini-computers. Innovations will take place almost daily as the microprocessor revolution continues. Now continue your studies by returning to the unit activity guide and following the instructions given there.